Welcome back, Nature and Code. We have arrived at chapter 6, which is about natural selection. And natural selection has been dubbed the best idea anyone's ever had. And I think I would agree with that statement. So, natural selection is often equated with evolution. But as you now know, evolution is simply the change in allele frequencies in a population over time. And there are many forces affecting those allele frequencies, and we've looked at some of them throughout the chapter so far. Now, natural selection, though, does stand out because it is the only force that is capable of producing adaptive traits. And an adaptive trait is a trait of an individual that makes the individual well adapted to the environment it lives in. What does that mean? What does well adapted mean? Well, it simply means that, all else being equal, the individual is more likely to survive and produce offspring than it would without that specific trait. So I want to show you an example. So, there are many examples out there, and pretty much almost everything you see out in nature is typically the consequence of an adaptation, or certainly a mix with genetic drift and all these forces, but there's always an element of adaptation in there. And I want to show you a really striking example, and that's one of mimicry. So the example I'm looking for here is this leaf katydid, which is an insect that has quite a stunning phenotype. So if you click here on images, these are all leaf katydids, and as you can see, and by the way, actually, Google has a very nice feature, Google image search here, where you can click on search tool and then click on usage rights, and then you can just choose those that are labeled for reuse. So for example, if you click on this, here's a nice example that's posted on Wikimedia. So let's take a look at this. All right, so this is really a stunning image of a leaf katydid. So just to be sure what this is, right? This is an insect. I know you might be thinking you're looking at a leaf, but this is an insect here. These are the wings of the insect, and here are the legs of the insect. So this is stunning, isn't it? And as a bird flying by, you would have a really hard time seeing this insect, which you would otherwise like to eat for lunch. So this is clearly natural adaptation. This doesn't just happen by chance. And so so how does this tie into with evolution? Well, let's just take a look at exactly this example, and let's develop an example that is it's not exactly how it happened. It's a thought process of an example. But imagine this is your forest here, lush green. That's what it looks like from the top. And now you can sort of think of these leaf katydids here living in this forest. And let's imagine a world where they all happen to have yellow wings for some reason. It doesn't matter. Again, it's just a thought experiment. So they kind of stand out in the from above. And so birds would eat them because they would find them quite easily. So now this population suffers heavy predation by birds, but let's just imagine now that suddenly there's an offspring leaf katydid that has a genetic mutation. So now suddenly there's a new allele, a genetic mutation, and that causes the katydid to have green leaf. So this is one mutant here. So now what's going to happen? Well, basically what's going to happen is that the birds will continue to eat the yellow ones because that's the ones they find, but this one will be spared because the birds can see this one. Okay, so birds keep eating these yellow katydids, and then now when it's reproduction time, of course, the remaining yellow ones will still reproduce, but so will the green one. And because this is a genetic feature, the offspring of that green katydid, if we now ignore the complexities of to biparental mating and mixing and so on, they're more, much more likely to be green here because it's a genetically inherited trait. And so once again, the birds will come along and will feed on these katydids and will continue to eat the yellow ones. And then once again, once a reproduction cycle comes around, these will leave much more offspring than the other ones because they haven't been eaten. And so, as a consequence, this allele here that's causing these green leaves here will increase in frequency. And that is, of course, evolution, right? Because these alleles increased in frequency. That's the definition of evolution, a change in allele frequency. However, now, crucially, right, it is by natural selection. And that's new. Because so far, we have assumed that the alleles, we had A1 alleles and we had A2 alleles, they were equal with respect to, us picking them from a population. All that mattered was their frequency, but one wasn't better or wasn't, more picked more often simply because it had some benefit. That wasn't the case. They were equal in terms of their evolutionary fitness, and this is a key concept. Evolutionary fitness. So what does that mean? What does fitness exactly mean? Well, fitness is simply evolutionary fitness is the ability to survive and reproduce. And this is not an absolute value. It's a relative one. You compare it to the fitness of the other alleles. And if an allele has a higher fitness than other alleles, that simply means that it's more likely than the other alleles to survive and make copies of itself. And so as a consequence of this, as we've seen in this example with the thought experiment with the yellow and green katydids, an allele with higher fitness, and the green one was an allele with higher fitness, is then expected to increase in frequency in the population. And so then you get evolution by natural selection. And so far, we have in the book assumed that all the alleles were selectively neutral, so the fitness of the A1 allele and the fitness of the A2 allele, they were equal. Now, natural selection occurs when that assumption is violated, okay? Then you get natural selection when you have differences in the fitness. All right, and I want to implement this in code right away. So go to your text editor and open this file that we developed in chapter 3, Drift HTML. So here's this file, and what you can see here, what we did last was to implement this bottleneck here. So if you open this file in your browser, you should see this classical bottleneck drift simulation. So chapter 3 drift, open it, and here you see where we left off last time in chapter 3. So go ahead and basically take this code, save it, because we want to save it as something else. We want to save it here. We need a new folder. It's going to be chapter 6. Okay, and I'm going to save it as drift and selection.html. Save. Okay, so the first thing to do is to get rid of these bottlenecks. So pick this if-else statement here and get rid of it. And be sure to set here the var population size to n. So we won't have bottlenecks. It's always going to be, population size is always going to be n. And then be sure to set that here to, let's say, perhaps 2,000 over 200 generations. Okay, so let's save this. And now let's go and open this file here in the browser. So again, open file, but now we need to go to chapter 6, drift and selection. And this is, of course, now here just our regular drift simulation, right? And you can see that, you know, in about half of the populations, half of the simulations, the A1 allele tends to go to fixation. In the others, it tends to get lost. But you know, it's hard to see here within 200 generations. But we already know from all the simulations that we did before that in about half of them, A1 will go to fixation, and in about half of them, A1 will eventually get lost. So now let's have a tiny change here that completely changes the dynamic. And the money line is here in your next generation function, this line here, right? This is where we pick the alleles that make it into the next generation. And at the moment we say, well, the probability that the A1 allele gets picked corresponds to its frequency, yeah? And the probability that the A2 allele gets picked corresponds to its frequency, which is 1 minus p down here. So now let's just add a slight, you know, a tiny change. We're just going to multiply this term here, p, with 1.01, which means effectively that this term here is simply 1% larger than p, which means that we are going to pick A1 with a probability that is slightly higher than p, just a bit higher, in fact 1% higher than p, 1% of p. And correspondingly, we're going to pick A2 a little less frequently than we would based on its frequency alone. And so in other words, P now, or A1 I should rather say, A1, the A1 allele has a slight fitness advantage, a slight selective advantage. Okay, and let's save this and go to our browser. And before you reload, just again, take a look at this picture. This is the situation where the alleles are selectively neutral. They have the exact same fitness. Now when you reload, you should see this. And yes, that looks quite different. Now take a look at this. A1 will just go straight to fixation at all times. You can really reload this however many times you want. A1 will go to fixation. And that is because it has this fitness advantage here. It is picked just a little bit more than you know you normally would, based on its frequency alone, if there were no fitness differences between those two alleles. But because we added this slight change here, it gets a little bit of a boost, and that is this. You know, that is exactly what this fitness means. It's more likely to reproduce, to survive and reproduce and make it into the next generation. But just a tiny little advantage here will have this dramatic effect. Now, one thing I want to mention, though, also because we already have a drift simulation here, because this is still right a finite population size. So the effect of drift is still here. And this is also why this example is called drift and selection. Both forces are now here affecting the evolutionary dynamic. You might say, well, but isn't drift simply when alleles start sort of going up and down in frequency and everything is chance? Yes, that is drift alone. But many cases, in practically all cases, you have drift and selection working together at the same time. Now, to make that example perhaps a bit clearer, let's put here P. Let's start P not at 0.5 but at 0.1, or let's start at 0.1. Go back to the simulation, and so you can see here that it will still go to fixation in almost all times. But there are some simulations where it's actually not totally clear what exactly will happen. It doesn't quite go straight up as it did before. And that's because down here in this area where the allele is quite rare, the effects of drift, which you can see quite nice here actually with these fluctuations, even on this upward trajectory, might eventually, just by pure chance, push it down to 0. And this hasn't happened yet here, but almost happened here. If you reload this frequently enough, it will eventually happen at one time. But another way to do this is to just start this at a lower frequency. Let's just start this at 0.05, so at 5%. And let's reload this a couple of times. And here it's happened, right? So despite having a selective benefit, a slight selective benefit, the allele still was outcompeted by the A2 allele. So just because an allele is selectively beneficial doesn't mean it automatically will go to fixation. In the case of finite population sizes, in the beginning when the allele is rare, it can still, drift is still affecting the dynamics, and an allele can still be pushed to extinction. And of course, as we now know, this is especially true in the beginning when the allele is rare. But once the allele has reached a certain frequency, as you can see, for example, when you set this to 0.2, I mean, yeah, it's pretty much guaranteed that it will go straight to fixation. So this is evolution by natural selection. All right, so now that we have established what this is, let's develop a more quantitative understanding of the process. See you in the next video.